Now we're going to be looking at networks. And I've also included the VCA dot points for networks. So I'm not going to go through all of them, but basically we're going to be looking at shortest path problems. We're going to be looking at network representation. We're going to be looking at minimal spanning trees. We're going to be looking at flow problems. We're going to be looking at the Hungarian algorithm. And we're also going to be looking at forward and backward scanning for any project type questions, and also a little bit of crashing. So I'm not going to go through a lot of crashing today, but you will have a look at the basics of crashing. Okay, so what is a network? So like I said, a network is just another way of representing information. So we can have different types of networks. So first we'll look at just undirected networks. So undirected networks are ones which have no arrows, just lines connecting the different vertices. So these things, the individual points, are called vertices, or the vertex. And we have lines connecting the vertexes to represent certain relationships between the vertices. And those lines are called edges. And if we have an edge that's connecting one vertex to itself, it's called a loop. And if we have a vertex that's not connecting any of the other vertices in the network by an edge, it's called an isolated vertex. And the thing that we look at for vertices is their degree. So the degree of a vertex just refers to how many edges are connected to that vertex. And the vertex, so for example, in this one over here, So for example, this vertex over here would have a degree of 3 because we have one. So we have one edge here, one edge here, and one edge here. So 3 edges. So therefore the degree of this vertex will be 3. And this is an odd degree. So if it's an odd number, then it will be an odd degree. If it's an even number, then it will be an even degree. So for example, this one, what will be the degree of this? So we have 1 edge, 2 edge, and this is technically just considered 1 edge. So 3 again. So this will also be 3. This one, we only have 1 and 2, so 2 edges. So that's how you would denote the degree of a vertex. Okay. So now we'll have a look at the faces of a network. So the faces are just the regions connecting between connected vertices and edges. So for example, this entire thing over here, so this triangle, would be considered a face. And the number of faces in this diagram, for example, so just looking inside, would be 1 here, 2, 3, 4, 5, 6, 7, and then 8. And then we also consider the region outside. So for example, this is the region outside, a face in itself. So that would be 9 faces in total. So very straightforward. We're just counting the number of regions that are, sort of chunked off by the vertices and edges. Okay, next we're going to be looking at the features of different types of networks. So a simple graph, so this is an example of a simple graph, it contains no loops and no multiple edges. So multiple edges just means, for example, we have 2 vertices being connected like this. So this would be considered a multiple edge because we're having vertex 2 and vertex 3 connected by this edge and this edge. So that would be a multiple edge. So a simple graph will have no multiple edges, no loops, and the sum of the degrees of all the vertices are always going to be 0. Not always going to be 0, are always going to be even. So for example, this one, we have 2, 2, 3, 2, and 2, and 3. So that will be 12. Regardless of if they're odd or even, they're always going to, in total, add up to an even number if it is a simple graph. Next, we have a degenerate graph. So a degenerate graph is one where you just have isolated vertexes, no edges. And all the vertices are therefore going to have a degree of 0, and the graph will also and the graph will just have one face. Okay, so next we have an example of a connected graph. So a connected graph is essentially where there is a path between all the vertices. And what that essentially means is we have no isolated vertexes. And the number of edges that are required for any graph to be a connected graph, so we can have multiple edges, so we might have this, that will still be considered a connected graph, but all the vertices in the graph need to be connected to the network or to the other vertices in the network. So in order to work out the minimum number of edges required, that would just be n minus 1, where n represents the number of vertexes. If we have two different graphs almost, and they're connected by a particular line, so for example here, that would be called a bridge. This term doesn't really appear that often on the exam, so don't really stress about that one. Next, we have a complete graph. So a complete graph is a type of connected graph, but a graph in which each vertex is connected directly by an edge to every other vertex in the graph. So all vertices must be connected to all other vertices in the network. So this vertex here must be connected by an edge to this vertex, and this vertex. And to calculate the number of edges that are required, you will use this formula. So edges is equal to n minus 1 over 2, where n represents the number of vertices. So pretty straightforward. Then we have a subgraph. So sometimes we might not need an entire graph to do a particular type of analysis. We might just need a type of that graph. So a subgraph is essentially a part of that graph. So right now it's not that clear, but when we start putting actual information on the network, then it will make a lot more sense. But essentially this over here is the subgraph. So this over here is a subgraph of this entire graph over here. So very straightforward again. Next we have isomorphic graphs. So isomorphic graphs are just two different networks that represents this exact same information. So they have the exact same vertices, exact same edges, and the vertices have the same degree as well. So if we were to represent this network in a different way for whatever reason, that would be an isomorphic graph. So these types of questions appear really often on the multiple choice section. So again, just to sort of summarize, an isomorphic graph is the exact same network, just represented in a different way. So they represent the exact same information. Okay. Next, we're going to be looking at, what was that? So next we're going to be looking at planar graphs. So planar graphs are essentially a type of graph in which no two edges can intersect. So for example, in this graph, so these two graphs are again isomorphic, but in this one we have these edges crossing. So if we were to draw an isomorphic graph, so if we were to draw an isomorphic graph of this one to make sure it's planar, we need to make sure that we draw the edge with no intersecting. So we can just draw the exact same edge, just in a different way. And if we were to count the number of faces that a network have, we need to make sure that a graph is planar. So that means there's no intersecting edges. So for example, in this graph, this is not 1, 2, 3 faces. This is, we can't actually use this graph, so this one, to calculate the number of faces. We'll have to convert it into this isomorphic graph where we can clearly see the, the edges, and they're not intersecting. So therefore, it's 1, 2 faces only. So really important to make sure that the graph is that you don't have any intersecting edges if you want to count the number of faces. Okay. Okay, so next we're going to be looking at walks, trails, cycles, and circuits, because a lot of the time, networks can be considered as as sort of like maps almost, to represent the relationships between different sort of locations on a map. So first of all, we'll be looking at trails. So trails might just be a route that you might take where you're not repeating any edges and you're visiting vertices more than once, or you can visit vertices more than once. So for example, an example of a trail in this example would be A, B, D, C, E, B. So this is an example of a trail. We're not repeating any of the edges, but we are allowed to repeat vertices. So we repeated B 2 times. So that's the important thing, no repeated edges, but the vertices can be visited more than once. Next, we have paths. So a path is one in which you don't repeat any edges and you don't repeat any vertices. So for example, A, B, E, C, D. So you're not repeating any edges and you're not repeating any vertices. And for a path, you don't actually have to visit all of the vertices. Like A, C is a path as well, or A, B, or A, C, E is also a path. So just because some people get confused between a path and something that we're going to be learning later on. Next, we come to circuits. So circuit is essentially where you're not repeating any edges, so you're not passing through the same edge more than once, but you can repeat vertices, and you're going to start and finish at the same vertex. So an example of a circuit might be A, B, E, C, A. So that is an example of a circuit. Remember, you don't have to visit every single vertex. So a circuit is essentially, therefore, just an example of a path. So just a path in which you're not repeating any of the edges or the vertices. But you can repeat vertices. Sorry, therefore it would be an example of a trail. So you're not repeating any edges, but you can repeat vertices. But you need to start and end at the same vertex. And lastly, we have cycles. So cycles are essentially where you are going around the map, but you're not repeating any edges, you're not passing through the same edge more than once, and you're not repeating any vertex. You're not going to the same location more than once, except for when you are at the start and the finish. So a cycle must also start and finish at the same vertex, similar to a circuit. But here, the only difference is that you can't repeat any vertices and you can't repeat any edges. So here is just a sort of an example, sort of like a summary table, which you can put in your summary book. So it's really helpful. It gives you the sort of requirements for each of these types of travel terms. Okay, so now we'll be looking at specific types of paths and specific types of cycles and specific types of trails and specific types of circuits. So the two types of paths, the type of path that you will look at is called a Hamiltonian path. So a Hamiltonian path is essentially a path, but there are specific requirements. So here you must pass through every vertex. So you need to pass through every vertex exactly once. So you're not passing through any vertex more than once. You need to pass through it exactly once. And it's a walk. And essentially, you can't repeat any edges. You can't repeat any edges, and you need to pass through every vertex more than once. Sorry, not more than once, only once. A Hamiltonian cycle, however, is a type of cycle where we are visiting each vertex exactly once. So this is just an example of a Hamiltonian path, but here we are visiting exactly every vertex exactly once, and we must start and end at the same vertex. So here is an example of a Hamiltonian cycle. So A, C, D, B, E, A. So we're not repeating any edges. We don't need to pass through all edges. That's another requirement. We don't need to pass through all edges. We just need to pass through every vertex exactly once. Next, we have an Eulerian trail. So an Eulerian trail is essentially when each edge now, so not vertex, each edge is visited exactly once. Vertices can be visited more than once, so that's not a requirement. They can be visited more than once, and they will only exist in networks with vertices that have all even except true odd vertices. So we need at least two odd vertices. Not at least, but we need exactly two odd vertices in the matrix. So for example, in this one, vertex, which one is odd? So we have vertex C and vertex B. They're both odd. So 1, 2, 3, 4, 5. Yeah, so they're both odd. 1, 2, 3, 4, 5, and 3. So they're both odd here. So therefore, this will be an Eulerian trail. So all even except two odd vertices. So we need to visit every edge, and we can repeat vertices, but we don't have to. And the way that you sort of go about formulating an Eulerian trail is you start off with the vertex that is odd, and you end up with the other vertex that is odd. Because remember, there's only going to be two odd vertices, the rest must be even. So therefore, you will start with the one odd vertex, and you will end up with the other at the other odd vertex. So here is an example. So B, and then loop B, and then D, and then C, and then E, and then B, and then A, and then again C. So you start off with one odd vertex and you end at the other, but you must pass through every edge exactly once. An Eulerian circuit is just an Eulerian trail, but here you again must pass through every edge exactly once. The only other requirement is that you must start and end at the same vertex. So in this case, an Eulerian circuit will only exist if every edge is even. Sorry, not every edge, but every vertex is even. So if every vertex is even, then an Eulerian circuit can exist. So these are sort of the questions that you're going to get in the exam. They'll ask you, what is the requirement for an Eulerian circuit to exist, or whether an Eulerian circuit exists for this example. And sometimes they'll ask you to, give the sequence of vertices that give the Eulerian circuit, or whatever example. Next, we're going to be looking at weighted graphs. So weighted graphs are essentially a graph. So it's essentially a network where each edge is actually assigned a weight or a value. And the weight can represent a lot of different things. So it might represent distance, it might represent time, a lot of different possibilities. Most of the time it's going to be distance. So next we'll look at trees. So we will look at spanning trees. So spanning trees are essentially trees where all the vertices in the network are connected. So just a type of connected graph. A minimal spanning tree, on the other hand, however, is you'll only be forming minimal spanning trees if you have a weighted graph. So what will happen is you will use Prim's algorithm. So I'll go through Prim's algorithm. And by using Prim's algorithm, you're going to find the sort of minimal spanning tree, or the edges that have the minimum weight overall. And the way that you sort of use Prim's algorithm is you pick any vertex. So for example, I might pick this one, and you draw the edge that is of minimum weight stemming from that vertex. So for example, this one's 4, this one's 6, and then this one's 3. So I will draw a line over here, 3. And then from that vertex, you will draw a line to the next edge that has the lowest weight. So it's this one over here. So that's a 1 here. And then from there, you do the exact same. So you won't go back this way because you just went through that. So therefore, you might go to here. So to 2. And then you might stop there. Then you might choose another vertex. So this one over here. So essentially what a minimal spanning tree will do is it will connect all vertices, but it will be the minimum sort of weight. So overall, if you add the numbers together, it should be the minimum weight. So the Prim's algorithm basically works is you pick a vertex and then you draw an edge to another vertex from the one that's the minimum sort of weight. So for example, if you pick this vertex, it will be this vertex over here. Then you might pick another vertex, it will be this one over here. Then you might pick another one, it will be this one over here. And essentially you will get at a point where all the vertices are connected. And it's the minimum weight. Okay, so next we'll be looking at network flow. So network flow is essentially a type of question that you're going to get to in the exam, where we'll be looking at a type of flow of something. So it might be, for example, the flow of water, or sometimes you might get the flow of people, or the flow of, certain items or certain things. And the way that so it's a directed graph, and the way that it sort of works is you have a source and you have a sink. So the source is where the supplies come from. So for example, if you think about, for example, a plumbing system, it might be, a source of water under your house map. And the sink might be where you want the water to come, where you will be using it. And it must flow through all these pipes. And these numbers indicate the maximum capacity of each pipe, each second usually, or for a certain time period. So this 180 might say that 100 might sort of mean that 180 liters of water are passing through this edge every second. So that's what it might sort of mean. And the way that you sort of interpret this is, if 180 liters of water every second are passing through from A to C, but only 90 liters can pass from C to F every second, where is this rest of the water going to go? Because only 90 liters can pass through this point every second. And then from there, only 70 can pass through this pipe. So this is a way of calculating the maximum flow. So that's what you'll be using these types of graphs to calculate. So maximum flow is overall, what is the maximum flow of water that we can get each second? And the sort of requirements are, it must be less than the total of the pipes leading from the source. So it must be less than the addition of 180 plus 40 plus 210. So just as a requirement if you want to check your answer. And it must be less than this amount as well. So it must be less than, this amount. So 70 plus 140. So the total flow must be less than 210, the maximum flow. And we'll be looking at how to calculate maximum flow. The way that VCAL likes to sort of do this is by using cuts. So we'll make specific cuts, and I'll show you what a cut is in a second. So this is a cut. So it's sort of a line going from the top, all the way from the top to the bottom. It can't be like this. It can't be a loop like this. It has to go all the way from the top and all the way to the bottom. So for example, I've drawn two cuts here. So there'll be a variety of different ways that you can draw a cut through this graph. And what this cut is essentially going to do is it's going to block the flow from the source to the sink, and then that way you can determine what's going to be the maximum flow. So for example, and if we draw this cut over here, what you will need to do is you will need to calculate the capacity of each cut. And the way that you calculate the capacity of each cut is you look at you add up the sort of but capacities of each of the pipes that are going from source to sink. So you will add the capacity of this line, then you would add the capacity of this line, all the lines that it passes through, and then you will add the capacity of this edge. So after you add the capacity, it's 300. And essentially the maximum flow is the capacity of the minimum cut. So you will do a variety of different cuts to find the minimum flow. So this red one over here has a capacity of 300. It might be the minimum flow or it might not. But we've sort of already established that it can't be the maximum flow because it has to be, so if only 210 liters per second can actually go into the sink at any time, how can the maximum capacity be 300? How can 300 go to the sink at any one time? So it has to be less than 210, but we don't actually know. We can do a variety of different cuts. So we can do this one, we can do this one, a lot of different cuts. So just to give you an example, so we might do this cut, we might do this cut, we might do this cut. And the important thing to note is you're only going to add up the pipes that are going through this cut, so that are intersecting with the cut, and that are flowing in the direction towards the sink, not towards the direction of the source. So if we had a pipe, for example, like this, so if we had it flowing in this direction, you wouldn't add up the capacity of that pipe when you're calculating the flow of that cut. So really important to note. So if we draw a cut here, that's actually 210. And if you do a lot of different, so this is again a bit of trial and error. If you do a lot of different cuts, this cut would have the minimum capacity. So therefore this 210 is the maximum flow. And there'll usually be units associated with that as well.